Yeah, sure. Thanks, Lindsay, and thanks everyone for watching. My name's Carlos Souza. I've been in the software industry since the late 2000s. Most of my experience is working on web-based applications and with open source technologies. I've worked with languages like PHP, Java, Ruby, Rails, JavaScript, and started with Go a little over a year ago. And like Lindsay said, I'm the author for the Code School course on Go. And yeah, I'm very excited to be here to share with you all a little bit about the language. So today I'm here to talk to you all about the Go programming language. We'll start with the very basics of the language. So if you've never seen Go before, don't worry. After we've learned the basics, we'll speed things up a bit and look at some of its more advanced features like cross-compilation, concurrency, and parallelism, which are some of my personal favorite things about Go. So we'll go from 0 to 60, or as every other country in the world other than the US like to say, from 0 to 100 kilometers per hour. Cool. So first things first, what is Go? Go is an open source language created by Google with a focus on building simple and efficient programs. A couple of characteristics from Go that stand out immediately. First, Go is a compiled language, meaning we must run our source code through a compiler which reads that source code and generates a single binary or executable file used to run our program. Before generating the final binary, the Go compiler also checks our code to validate and optimize operations. It enforces rules on data types like integers, strings, and booleans, and it will raise errors if it sees that any of these rules are broken. And this is a huge time saver for us developers since it leaves less room for unexpected surprises when we actually run our program. This particular feature of Go places it in the category of statically typed languages. Now, programs written in Go are fast and can scale really well, all thanks to a concurrency model built into the language and quite easy to use, as we'll see shortly. Go programs, for the most part, are also easy to deploy. So because the compiler generates a single executable file, sometimes deploying Go programs to production can be as simple as copying the executable over to the server. Let's do a quick comparison between Go and some other popular programming languages. We've just talked about how Go is a compiled language. We write the source code, run it through a compiler, and then machine code is generated in the form of a binary file, which we transfer over to a server. The server that's running the program doesn't need to have Go installed. The binary that's generated from the compilation process contains everything that's needed to run our program. On the other hand, languages like PHP, Python, and Ruby are interpreted languages, also known as scripting languages. This means that we must install a runtime environment and ship the actual source code to production. Every time you run our program in production, the runtime will parse the source code, turn it into machine code, and then execute it. And that's why interpreted languages are generally slower than compiled languages. Now, languages like Java, C#, and Elixir are both compiled and interpreted. To run programs written in these languages, we compile the source code into bytecode, and then we ship the bytecode to production. Now, the bytecode isn't machine code, and we still need a runtime environment, in this case, a virtual machine like the JVM or .NET or the Erlang virtual machine in order to execute programs in these languages. The Go language is a great fit for cases where developers have no control over the production server. As we'll see in just a little bit, we can cross-compile Go programs to run on a variety of different operating systems and architectures. Once compiled to machine code, the binaries can essentially be transferred over to the destination server and run without having to install anything else. Now let's do a quick poll. In your day job, what type language do you work with primarily? Compiled only language, interpreted only language, or a language that's compiled and interpreted? I'll give you all a minute to answer. Give you a couple more seconds. Everybody place their answer in the poll. All right, let's look at the results. All right, so almost 12% of you all work with a compiled only language. Almost 20% work with a language that's interpreted only. And the vast majority works with a language that's compiled and interpreted. Very good to know. Cool, let's move on. Now, the next question that we want to address is, what types of programs is Go a good fit for? And the answer is systems programming. Systems programming is the type of programming aimed at servicing other systems, as opposed to servicing users directly. These lower level programs, more often than not, won't even have a graphical user interface with links and buttons and forms. Instead, they run straight from the terminal or the command line. Examples of these system programs include operating systems, APIs, game engines, and network applications, just to name a few. These are usually resource constrained and must perform extremely fast, and that's exactly where Go shines. Now, programs that provide services directly to users, like web applications, music players, or text editors, are called application programs. Now, Go can also be used to build those, but it's less common. Let's dive into some code now. The first Go program that we'll write is a simple hello world. We'll use a single source file that, once compiled, will generate an executable which we can use to run the program, and we'll see this message printed to the console. Hello, I am Gopher. Now here on the left is a typical Go workspace. We have our Go path, and then inside of it we have the source folder, which is the root of all our Go source code. We create a new folder for each separate project. In this example, we'll call it Hello. Under the new Hello folder, we can find a Go source code with a .go extension. Now, since this Hello World program, we have a single file, we'll call this file main.go. But this is a naming convention, not a rule. We could call this file anything. Inside our main.go file, the very first thing we write is the package definition, package main. Then we define the main function, which is the entry point for all our Go programs. All Go programs must have a main package and a main function. In order to write to the console, we'll need to import a package from the Go standard library called FMT, which stands for format. Package imports go after the package definition. Then, from inside the main function, we call the printline function from the format package, giving it the string, hello, I am Gopher. Notice semicolons are not necessary in Go. And this is all the code that we have to write for now. So let's see how we can run it. Remember we talked about a compiler reading the source code and then producing an executable file? Well, this process of reading the source code, resolving package dependencies, and producing the executable file is called a build process. In order to build our Go project, we use the build command, shift with Go. We run go build from the project root, and the compiler produces an executable file named after the project with no extension. Using that file, hello, we run the program, and we can see the message printed to the screen. Hello, I am Gopher. Now, for those with a background in interpreted languages like Ruby, Python, or PHP, you might be wondering if there's a way to run Go programs without this intermediate compilation step. And the answer is yes. We can use go run, another command that's shipped with Go, and give it the main file name. With this single command, our program will be built and run, and we can see the same message printed to the console. Hello, I am Gopher. Now, while we rarely use go run in production, this command is quite handy for development. Now our demo. We'll write a command line program that takes one argument supplied by the user, a string. The program will read this string and will write it to a text file in the file system. First, we'll write this program on a Mac and run it on the same machine. Then, using the same source code, we'll cross-compile the program to run on a Linux machine.
So the first thing that we're going to do is create an empty main.go file. Then, using Visual Studio Code, we're going to open that file. Visual Studio Code is my preferred text editor for writing Go programs. So we declare the main package and the main function. Now the first thing that we're going to do is read command line arguments passed by the user. So we're going to use os args to read the arguments and assign it to an empty variable args using automatically type inference with the := sign. Then we're going to check if the length of the arguments is equal to 1. And if it is, we're going to log an error. Please provide message. And this is because the first argument to a Go program is always the name of the program itself. The actual user supplied argument is the second argument returned from the os.args slice. So that's what we're going to assign to the message variable. Now, next thing we're going to do is actually create the text file that we're going to write our message to. And to do that, we're going to, again, use the os package and the create function. So we're going to create a file called file.text, and then the call to this function returns two things. One, the file handler, and the other is a potential error. Now, if there is an error, we are going to, again, print a message to the screen saying error, creating file, and we'll immediately exit the program. Now, what we want to do every time that we open a file, we want to make sure that we close this file, the file handler, so that we don't consume a lot of RAM from our servers. So what we could do is write a call to the close function all the way to the end of the main function so that it closes once we're done working with it. But Go allows us to do this in a more friendly way, which is using the defer keyword and passing it the function that we want to be called at the end of the enclosing function. So what that means is that although we're writing defer f.close on line 20, the f.close function will not be called until the main function is done executing. which is really nice. Now moving on, what we want to do with our file handler assigned to the f variable is use this handler to actually write contents to the file. So to do that, we're going to use the write string function, giving it the message. And again, what we get back is the number of bytes that were written to the file, which we want to ignore, so we're going to assign it to underline, and we also get a potential write error back. So we're going to do the proper error handling, and if there is an error, we are going to exit from the program and write a message, error writing to file. Now lastly, what we need to do is call a function to flush the contents of the file to the actual file system. So we do that using f.sync, and that's it. So let's print a message saying that this is done. So this is all the code that we need to write. Now let's go back to the terminal, clear our screen, and as you can see, all we have right now is the main.go source code file, and we are going to build this file. Once we run go build, we can see that now we have a binary that was generated for us. And we can run this binary and give it a message, hello from Go. When we run this, we can see that now we have a file.txt file, and if we look at the contents of this file, we have our message. Now, this file only works on OS X machines. On this other tab, I am running a Linux operating system. As you can see, it is an Ubuntu machine. So if we try running the same binary on our Ubuntu machine, over here, we will see that it doesn't work, because this binary was not produced for a Linux machine. Now let's go ahead and do that. Going back to our OS X development environment, we're going to cross-compile our Go program on, again, an OS X development environment to run on a Linux environment. Now to do that, we're going to use some flags. First is the Go OS flag, saying we want to compile this to a Linux machine. Then is the Go Arch flag, saying the architecture that we want to compile this to. Then we run go build, giving it the name of the output file. We'll call it webinar Linux, and then the source code. We run that, and then we can see it generated another binary for us, webinar-linux, and if we inspect the type of file, we can see it's a different file. It's an LSB executable. Now we're going to move that file to our Linux box, move over to our Linux box. We can now see that our file is there, and then we'll run it, giving it the message, hello from Linux. We can see it runs as expected. It produces the file.txt file as expected and writes the content of our command line arguments, hello from Linux, to that file, hello from Linux.
All right, now let's talk about concurrency and parallelism. One is not like the other. Consider the following search engine, Big Search. Big Search allows us to type in a keyword and it'll search the web for three things: websites, images, and videos. Depending on how Big Search is implemented, there are a couple different ways the search can happen. In sequential programs, for example, before a new task starts, the previous one must finish. If Big Search was coded this way, here's one way it could behave. It would start with the first search, say website. Only once that was finished, it would move on to the next search, images. Then once that was complete, move on to the last one, videos. The total time will be the sum of all the tasks. So if the search for websites took 2 seconds, images 3 seconds, and video 4 seconds, then the total search time will be 2 plus 3 plus 4, so 9 seconds. In concurrent programs, multiple tasks can be executed independently and may appear simultaneous. If Big Search was programmed this way, we'd see results from websites, images, and videos showing up in what would appear to be the same time. Under the hood, each search would be split into small chunks, and those chunks would alternate execution. The total time would still be the sum of all the tasks, 9 seconds. But tasks would alternate time slices, giving the impression they're running together. Finally, in parallel programs, multiple tasks can be executed simultaneously in multi-core machines, or machines with multiple CPUs. If Big Search was run as a parallel program, then website, image, and video searches would all be performing at the same time. And the total time for search would be the time for the slowest task. As we can see here, videos is the slowest task, so the total time of the search would be 4 seconds. I know this might be a little confusing if this is the first time that you're hearing about it, but the important thing to remember is that concurrency and parallelism are not the same thing. Concurrent means independent, which is a necessary step towards parallelism, which means simultaneous. Go's concurrency model and Go routines make it simple to build parallel programs that take advantage of machines with multiple processors, which are most machines today. And we don't have to use threads. We can work with a higher level of abstraction, which leaves less room for errors. Now on to the second and final demo. This one is going to be another command line program that loops through a collection of names and prints each one to the console. We'll write a print function which will intentionally require a lot of CPU time before printing each name to the console, and then we'll see how we can use Go routines to make our program run faster.
We're going to start with a very simple example. First, we're going to create an empty file, open it with Visual Studio Code. Then we'll declare our main package and our main function. Then first thing we're going to do is we're going to create a slice of strings and assign it to the names variable. And we're going to give it some states from the US. So Florida, Colorado, and Georgia. Next thing, we are going to loop through these strings and simply print them to the console. So we're going to use the for loop underscore because we don't care about the index. All we care about is the name itself, range, and then we're going to call a function called print name and give it the name. Now, of course, it's showing an error because we have not declared this function yet. So we're going to go ahead and do that. Takes a string, and then all it does is prints this string to the console. Cool. So if we go and change it over back to our terminal, and run our program, we can see it prints super fast. Now, to print the time that it takes to run this program, we're going to use a Unix tool called time. So we're simply going to call time and run our program again. And you see it prints how long it took to run the program. So about 200 milliseconds. Now we're going to go back to our program and we're going to add a processing that's going to consume quite a bit of CPU processing time. So I'm going to go ahead and paste this code. It's a fairly complex math operation that's going to loop 200 million times and execute this operation. Now, this is going to take quite a while. So let's save this file and run it again. So let me clear the screen first and run this again. And you'll notice now it's taking a lot more time than before. Let's see the total time. So it takes about 8 seconds to run the entire program. Now we're going to add concurrency and see if we can improve the runtime of this program. So we're going to go back to our main function and we're going to declare a variable called WG of the type sync wait group. So this WG variable gives us a couple of different methods that we can call to use what we call Go routines, which are lightweight threads offered by the language that allows us to run tasks concurrently. So the first thing we need to do is to tell the wait group how many Go routines we're going to be running concurrently. And we do this with the add method. Now we could simply say 3 because that would be one Go routine for each element inside of our named slice, but we're going to make this more dynamic and just return the length of the named slice. So that way, if we add any more elements to the slice, we don't have to change this line. Now, we created the wait group. Now, what we have to do at the end of the main function is tell the main function to wait until all the Go routines are done executing. Otherwise, our program is going to run, and once it hits the end of the for loop, it's going to quit before the Go routines are done. Now, the next thing we need to do is to pass the wait group as an argument to the print name function. And we're going to pass a pointer to the wait group. And on the function signature, we need to tell that we are receiving a pointer to a wait group. And what we're going to do is we're going to defer the call to done. And this means that after each call to print name, we are going to call the wg.done method, which tells the Go runtime that this specific Go routine is finished executing. Now, one last thing that we have to do is to tell the runtime that each call to the print name function needs to run inside of a Go routine. And we do that with the keyword Go. Now, when we go back to our terminal and run our program again, we can see that it takes a lot less time to run, about 3 seconds, a lot faster. Now, here's one thing that's really cool. I'm going to run a program called how-tos, which shows all the processes running on my machine, as well as the consumption of each core. And you can see here I have 4 different cores on my machine. Now, when I run my program, we can see that all the cores are running, and our program takes about the same time, 3.8 seconds, 4 seconds, around the same time. Now, by default, Go uses all the available CPUs on the machine. Now, if you wanted to limit the amount of CPUs that we wanted to use, we export a variable called go-max-prox. Now, go-max-prox, since I have 4 different cores on this machine, it defaults to 4. Now, if I want to tell it to run on a single core,
then I can tell go maxprox equals 1 and run it again. And then we'll see that it's no longer using all 4 cores and it's taking a lot more time to run. So, yep, back to the 8 seconds originally, because although our code is concurrent, it's not parallel because it's not able to leverage more than 1 core at the same time.
All right, before we wrap this up, I'd like to mention a couple of recommended courses and resources that you can go to learn more about Go. The first one is Code School's On Track with Golang. On this course, you'll get to watch short videos about the most popular features of Go, and then after each video, you get to test your knowledge by taking coding challenges in the browser. No setup is necessary, so you don't have to install Go on your computer. All you need is a browser. Also, in Pluralsight, we currently have other 14 courses on Go. And these include courses on the language, as well as courses on frameworks and more advanced techniques. And that's what I had to present to you today about Go. Down below, if you have any questions, you can send through the web tool, or you can reach out to me via my email address or via Twitter and GitHub. My handle is up on the slide, and also the source code for the demo apps that we showed in this presentation is available on this GitHub URL down below. All right, so we have a couple of questions here, so we're going to go ahead and start answering them. The first question asks about major projects that use Go. That's a great question. So a couple of products that actually use Go, one of them is Docker, the container technology tool, and also Kubernetes, which is the deployment tool for Docker. And there's a lot of companies using Go, like Google, who created it, IBM, VMware, Facebook, Heroku, SoundCloud, BBC, DigitalOcean, Cloudflare, CarOS, Dropbox, and just to name a few. So next question, what are some of the advantages of Go over a language like Java that also supports deployment of multiple platforms? So as we've covered in the beginning of this presentation, Go compiles to a binary, as opposed to languages like Java that compile to bytecode that needs to run on top of a specific runtime, or in the case of Java, the Java virtual machine. So if you're a developer and you don't have access to the production environment, then Go is an interesting alternative, because all you have to do is transfer the final binary over to production, and you know it's going to work, as opposed to when you compile a Java program on your development environment, you still rely on having a runtime installed on the production server in order to run your program. Now, the JVM is extremely powerful, has been around for many years, and it's fine-tuned for performance, which is fine, and it might work in a lot of cases, but on the cases that you need more control over the server, you might want to go with a language like Go that you can cross-compile to run on a different machine in architecture. So another question asked, is it the same executable for all operating systems? And the answer is no. We showed in the demo that depending on where you're going to run your program, you need to set some environment variables when you compile it. That's what we call the cross-compilation. So you can compile, you can use a development environment and then tell the Go compiler to generate a binary for a specific target environment. So the first example we compiled to run on an OS X machine, and then as we saw on the demo, that same binary was not able to run on the Linux machine. So we went back and tweaked some of the environment variables, then generated a binary specific for a Linux operating system and AMD 64 architecture, which then was able to run properly on Linux. Another question, can I have multiple .go files And do they each need the main method? And the answer is yes, you can have multiple Go files in a project, and no, not all of them need to have the main method. The only file that needs to have the main method is the entry file, the entry point of your application. All the other files don't have to have the main method. And also, if you're writing a library for distribution, say a package that you want other people to use on their programs, then you don't need the main method at all. Another question, could Go be used to serve web pages? And the answer is yes. Although Go is focused on systems programming, you can still develop web apps and web pages using Go. I personally think other languages are more suited for this, but yes, you can still use Go to write websites. Another question, can Go be used for developing graphical user interface apps? I am not sure. I want to say yes, but I haven't done that, so I'm not really sure about this one. Another question is, what is the state of Go's standard library? And the answer is it's very stable. Over the previous major releases of Go, we haven't seen a whole lot of changes and very little to almost no breaking changes. So it's very stable. And what is great about it? So what is great about it, once, its stability is great about it. And also that when you're writing Go programs, you'll find yourself not relying a lot on third-party libraries. The standard library has pretty much everything you need to get going on most applications. So another question is, what are some typical use cases for Go in an enterprise setting? That is a very good question. So also known as like brownfield, when you have existing apps that you need to integrate Go with. So I'm going to go back to the feature of Go that allows it to be cross-compiled. So when you don't have a lot of control over the production environment and you want to add features to an existing app, you could use Go to write an API that another existing apps can plug into over, say, HTTP, which again is the library, is a package that comes in the standard library. So to write a web APIs in Go, you don't have to include any third-party dependencies. The HTTP package is part of the standard library, so that would be a good use case. So to add existing features to add new features to existing apps, you could use Go. Pretty nice. So another question, could Go generally be used to replace typically Node.js applications? The answer is yes. Now, whether or not you want to replace them or the reasons why you might need to replace them will vary depending on your context. But yes, you could write Go programs that replace Node.js applications. Is Go an object-oriented programming language? No, it's not. In Go, we don't have objects, we don't have classes. We have methods, and then we have structs. In that sense, Go is similar to C. Another question, is there an HTTP server written in Go? The answer is yes. There's a library out there called, there is an HTTP server out there called Caddy that's written in Go. And again, like I said, Go comes with the HTTP package as part of its standard library. So with very few lines of code, you could write an HTTP server in Go without any third-party dependency. Another question is, what makes Go suitable for microservices architectures? So this is a great question, and a couple of things I think that make Go suitable for microservices architecture. We mentioned a couple of these in this presentation, which is first, the syntax is is quite easy to understand. It's not a very complex language in terms of syntax, so it makes it easy to write programs. And the fact that you can cross-compile it to different architectures and generate a self-contained binary makes it easy to deploy services to production. So I think those are pretty good reasons. And to add another one would be the concurrency model. So again, it's part of the language. You don't have to include any third-party dependencies to write Go programs that leverage concurrency in parallelism, that leverage all the CPUs of a server. So what platforms can you develop Go for? I don't have the list here, but the website is pretty good at listing the platforms that the compiler runs on, and also the platform that the compiler will generate binaries for. So I want to say most of the major platforms are supported by Go. Do we have data science library in Go? That is a very good question. I want to answer this question referring you to a talk from last year's GopherCon. So GopherCon 2016, there was a talk devoted entirely about data science in Go. So I don't remember the name of the library, but the speaker, the presenter for this specific talk, he went over techniques for data science and also some of the libraries he used for writing data science programs in Go. So check out GopherCon 2016. I'm pretty sure the videos are up on YouTube. So we're going to go to the last question. Let's see. So how does Go compare with other systems programming languages like Rust and C? So some of the people that developed Go were also part of the development of the C and the evolution of the C programming language, and they like to say that Go is kind of like the next step from C. It's easier to write Go programs than it is to write C programs. There's less things that you have to worry about when writing programs in Go. One example is threads. So if you're writing concurrent and parallel programs in C, you have to manually manage threads, as opposed to Go, that gives you a higher abstraction in the form of Go routines. As far as comparison with Rust, I don't know. I have not worked with Rust yet, but I hear that, again, compared to Rust, Go is a little bit easier to understand as well. So that's it for this presentation. Again, if you want to reach out to me, my contact information is up on the screen. You can reach out to me via Twitter or sending out email. The source code for the apps that we wrote today in this presentation are available on my GitHub. And with that being said, I'm going to hand it back to Lindsay. So thank you very much for watching.
Awesome. Thank you so much, Carlos, for presenting. Thank you for taking so many awesome questions, too. And thank you, everyone, for joining us today and taking time out of your day to learn more about Go. So we are going to close out the presentation here in just a second. We have recorded everything, and we're going to share that recording with everyone. Just give us a few days to put that up on our website. We'll also send out the links that Carlos shared with everyone to his GitHub, the course, and anything else that's helpful to help you get started as you learn more about this language. So as I close out today, I'm just going to share a brief little video. We made a very exciting announcement this week for our first in-person conference coming up this September. So I'm going to close out with that and end with the link. You are very, very, very welcome to check it out and then come meet us in person and learn more about everything that you are working on and trying to master in your career. So I hope everyone has a wonderful day, and thank you for joining us.